is it has so this is the pit of the rattlesnake, and so it has this little tiny membrane here, which is very, very highly innervated. So it's got these big nerves that come in. But because it's an infrared sensor, this is kind of like a second retina for this rattlesnake, and so you can't have much mass. If you have a lot of mass, you can't get enough temperature rise to sense it, see? And the rattlesnake has to grab these infrared photons. So the rat that's wiggling around in front of the rattlesnake, those photons that it's emitting are in the 10 micron band. So they're not very energetic photons. And so you've got to have low mass in this membrane, in this pit. And so if you look at it, the pit actually looks like an eye. It has no lens, so it's not like our eyeball, because if you have water's going to absorb the infrared light. So you can't have a cornea, you can't have a lens. So basically you have this pit where the nerve just comes out. And you have just like these 10,000, 100,000 nerve endings in this, it's called the terminal mass. These are some TEM images that one of the graduate students took. But this gray mass here, these are all the receptors, the thermal receptors that are in this pit. And you can see, here's a big old nerve that comes up, and you can see how it divides, and divides, and divides, and divides. And it basically has just this tens of thousands of little sensors that get put in this sheet that allows the snake to be able to see infrared light. So this is actually one mechanism that nature has evolved to be able to see infrared images. This actually turned out to not be the most interesting. The absolute most interesting thing that we ended up studying, actually spending most of our time with, was a little critter called Melanophila acuminata, which is also known as a fire beetle. Okay? I don't know if y'all have ever heard of a fire beetle, but what this is, people, for example, in Colorado and Wyoming, they fight these big forest fires. And whenever there's a big forest fire, these fire beetles, they all swarm to the forest fire. And a lot of times they can be really obnoxious because they get on your gear and you can't see, and just get millions and millions of these fire beetles. It turns out that a fire beetle can sense a fire. We know this is a fact. Can sense a fire 500 miles away. That's pretty incredible. And what's even more incredible is they also have an infrared sensor that allows them to actually see the fire. And so they can see the heat that's rising up from the fire. And the reason it's important to this fire beetle is because the male and the female have to meet together on a simmering, just almost burning log and copulate in order to be able to reproduce. So you talk about sex in a hot place. These fire beetles, in order for them to survive, they got to meet at this forest fire while the fire is just still simmering. And then the female lays her eggs, and then the next generation goes on. And so it turns out, when we study this, it turns out that these fire beetles have this really kind of a neat structure, which has an infrared lens. This is an infrared lens which focuses the light onto this bare nerve ending. This is a nerve ending, okay? And what happens is infrared light gets amplified into it's called a sensilla, but you have an infrared lens, and what happens is this whole device, it moves like this, okay? And what that does is it puts mechanical pressure on that nerve ending. And so this is a real interesting sensor. It goes from light energy to heat energy to mechanical energy that then is transduced in the nerve that goes to this bug's brain and tells us that it saw something that was hot. And so this is a very interesting example of what's called a mechanical sensor. And actually we use this design to actually design a device called a microbolometer. And so a lot of the infrared sensors, even today, if you buy an infrared camera, they'll have in them a sensor which is based on the same principle of the microbolometer. It's fashioned after this little fire beetle. Any questions? That's how you can do what's called biomimetics. It's biomedical engineers. Any questions about pain and temperature? All right, the second thing that we're going to talk about today is called conscious proprioception. So conscious proprioception, unlike pain and temperature, okay, is something that tells us stereognostic sense, okay? And so if I, were to come up and give you something, I like to pick on you, you look so cute. Don't look, you can't look. I'm going to give you something, I want you just to feel it. You don't look, you tell me what that is. Okay, feel it, feel it. How many things do I have that I've given you? 3 things, okay? And they are paper clips. Well, you're pretty close. It's safety pins. And they're all kind of stuck together. They kind of feel like paper clips. But she could tell exactly how many. That's stereognostic sense. She can feel this, and she can tell what it is. Okay, that's stereognostic proprioceptive sense. Okay? It also, the way actually we test this is with vibration, okay? And so clinically, if I'm testing your proprioception, I'm going to take this and I'm going to let you tell me if you feel the vibration, okay? So, let me show you how this works. Let me see your hand for a minute. Feel it? Okay. You see, I can test. You can feel the vibration. That's actually our low-tech way of doing this sensory test on proprioception. So basically this allows us to have what we call 2-point discrimination. Unlike pain and temperature, this allows us to tell something that we have in our hand. So we can test our environment. You know, if it's in the dark, so I'm sure if I'm in the dark and you find something, you can fill in a box and you can figure out what it is. So it's the same kind of thing. So the concept here that's really important is this concept of what's called a receptive field. It turns out that we have different sizes of receptive field. And so any part of our body where we have a lot of neurons that go to whatever that sensory sheet is, whenever we have a very high innervation density, we're going to have very, very small receptive field. And so the smaller the receptive field, the better the 2-point discrimination. And it's not a hard concept here, but if I have one big neuron that has a huge receptive field like here, okay, I'm not going to be able to discriminate as much as if I have a whole bunch of smaller ones. So this would be an example of really big, next big, and this would be really good. So this is really good 2-point discrimination. Okay? So the smaller the receptive field, the more neurons, the higher innervation density, smaller receptive field. And the way we test this is actually just to use we can actually do it with our fingers, we can do it with a compass. Basically, it's how far apart can I move the stimuli and you still be able to sense that it's 2 instead of 1. And so if I have the same distance between the 2 points that touch you, if I have large receptive fields, you will sense this as 1. And in this case, you will sense this as 2. Okay? And so this is how we test, 2-point, what we call 2-point discrimination. And it all has to do with the size of the receptive field. So on our back, we have quite large receptive fields.
Yeah. I was going to ask a question. So a few years back I had knee surgery and they made a cut in the middle of the knee and now I've got a giant numb spot on like the left side of my knee. Does that basically mean that I lost like that sense on that area?
You have, exactly. You've lost that sensory supply. Cool. not real cool. So anyway, so like on your back, you're going to have these rather large receptive fields, but maybe on your fingertips, the receptive field is going to be smaller, and so you can actually tell the 2 points as opposed to 1. better on your fingertips than you could on your back. We know that this is kind of generalized. The forearm, the back is even worse, but the forearm has about 4 centimeters in terms of the difference between the centers of the receptive fields. Back of your hands a little bit better. Your lips are a lot better. Fingertips are even better. But really, really good is your tongue. Okay? Think about it. Why do you need good 2-point discrimination in your tongue? And don't think reversed. Why do you need good 2-point discrimination in your tongue?
Still fighting.
What do you do in your mouth usually? Chew. You eat, right? So why is it important for people to tell us you don't want to bite your tongue, but what if you ate something that had a bone in it? That's not good, is it? Right. So I mean, you basically want to be able to tell if you've got sand or bones or who knows what might be the food you're eating, right? So there's a survival advantage to being able to tell, sense something about what it is that you're eating. And that's why your tongue has good 2-point discrimination.
So I know this is proprioception, and it's not like pain, but is there a correlation with how proprioceptive something is to how pain sensitive it
No,
is?
they're totally different. Your brain perceives these as totally different systems. And since you like to ask questions, I want you to, I'm going to say something. It's another party trick. So I need you to take your shirt off. So again, the way we test 2-point discrimination is to use 2 points, right? Okay. And so I can test with 1 finger, I can test with 2 fingers, and he can kind of tell the difference. Now between those 2, it becomes a little trickier. Okay. So I just want you to tell me 1 or 2. Okay. You see that? So he can't discriminate that far apart. Okay, so we keep doing it. Okay, so 2. See, so about that far apart he can discriminate. So about 2 or 3 centimeters he can discriminate, but he can't discriminate if I go smaller than that. Okay, let's give you a big hand. Okay, now if you want to get the absolute best 2-point discrimination, the very best 2-point discrimination is actually in your retina. So your photoreceptors are spaced about 1 micron apart. And so it turns out that actually because of the processing that occurs in your retina, you can actually get down to about 0.2 micron. You can actually get down to kind of the optical resolution limit, the diffractive limit in the eye, simply because your spacing of all the photoreceptors is so close together to your retina. Good twist question. Which has the best, list all these things, has the best 2-point discrimination with the retina by 4. Now the central pathway for proprioception, yes?
Sorry, so that, when you say 1 micron 2-point discrimination,
Right.
is that for visual or is that touch as well?
Okay, so the way, actually we do test this, and so the way that we test this is by taking 2 spots of light. Okay, and so I can take 2 spots of light, and if I get them closer than 1 micron, you start seeing it as 1.
Okay.
Okay, and then I get to about 1 micron, and you can actually start, seeing that it's 2 spots of light instead of 1.
Okay. So everything above the retina, that's all touch. Like
Yeah. Well, the retina's going to respond to light. The skin's going to respond to mechanical stimulation. Okay. But the same principle works in the ear. So in the cochlea of your ear, you get what's called tonotopic discrimination. And basically, again, it breaks down into your 2-point discrimination on the vascular membrane of your cochlea. And so it's the same principle applies in all of our sensory systems. Same principle. Okay, and so the central pathway is called the posterior column medial lemniscal pathway. And this pathway, which you also need to commit to memory, is a pathway which is only 3 neurons, with the primary neuron, again, being in your skin. And unlike pain and temperature, this pathway goes all the way up to the brainstem. It does not cross on entry. Okay, big difference. So this goes all the way up to your brainstem. Okay, then it crosses over in the internal arcuate fibers, and then ascends on the opposite side to the VPL thalamus, and then the third order neuron goes to the postcentral gyrus of the brain. So this pathway, more realistically, comes in. So here's your primary neuron here. It comes in and it ascends in this area here, which is called the posterior column. That's the posterior column of the brain, of the spinal cord. So this is called the posterior column. This is called the medial lemniscus. So it's the posterior column medial lemniscal pathway, 3 neuron pathway that goes to the postcentral gyrus. So this is the area 3, if you remember Brodmann area 3. So again, here's the sensory information coming in. It stays on the same side, goes all the way up to the brainstem, to the medulla. Then it crosses and then goes up the opposite side in the lemniscal pathway up to the VPL thalamus and into the cortex. So it's a totally different pathway. It's totally separate from pain and temperature. So your ability to perceive vibration, 2-point discrimination is, again, completely different connectome, completely different pathway from pain and temperature. When you get up to the postcentral gyrus, you have what's called a homunculus. And basically this is kind of a pictorial, a cartoon representation of how much your brain is devoted to looking at that part of your body. And so as you can see, we get a disproportionate representation for our hand. We get a disproportionate representation for the face, much more than we should have for the tongue, for the lips and for the tongue. The tongue gets a huge amount of representation compared to the amount of area. So the tongue, the face, the lips, get a lot more in your hand, and your thumb, particularly your thumb and your hand, get a lot of representation, simply because this is so important for your brain to be able to process that information. So there are 2 diseases that affect the posterior column that you need to know about. The first one is called combined subacute degeneration. Okay. So combined subacute degeneration is a disease that is associated with pernicious anemia. And so this is actually fairly common. If you, for whatever reason, can't absorb B12, you have some gut issues, you don't get enough, whatever. So this is actually B12 deficiency. You will get a defect, you will get a problem with your ability to process the stereognostic sense. Okay? The second disease that you need to be aware of is a disease which is associated with the oldest profession in the world. I don't know what the oldest profession is. All right. Y'all are really sharp. Y'all are really sharp. I have to admit. So the second disease that commonly destroys the posterior columns is neurosyphilis. So these are the 2 diseases that you need to know about that can cause a problem with the posterior column pathway. And in both cases, you lose the ability for proprioception. I saw a patient yesterday, actually, that had Charcot-Marie-Tooth, which is another form of posterior column degeneration. We talked about this a little bit last time. fact, I was visiting with Heather today. We talked a little bit about that. So anyway, there are some other diseases. Charcot-Marie Tooth is also called perineal atrophy. And so if you lose proprioception, you lose the ability to tell where you are in space. And so another way we actually test proprioception, other than the tuning fork, you just have somebody close their eyes. If you close your eyes, you basically are left with your vestibular system and your proprioceptive system, which tells you where you are in space. And somebody that has a deficiency in the proprioception pathway becomes quite unstable when they're upright. And so we can also test it by just simply having somebody close their eyes, put their arms out, and see if they can stand without falling. You lose that ability. So this lady I saw yesterday with Charcot-Marie Tooth disease, she couldn't stand with her eyes closed. So in order to stay upright, you have to have vision, you have to have your vestibular system, and you have to have the proprioception. Yeah.
You say, the first one, you said you're not able to process the scary gnostic sense. So is that just being able to tell what an object is when you feel it, or is it like trying to imagine the object?
No, it's not imagine. I give you something, you tell me what it is.
Just by touch?
Touch.
Okay,
You tell
that's
what
it.
it is by touch. If you can't, close your eyes, pick something up and tell what it is, then you don't have proprioception. Okay? Is there another question? Okay. So let's look at our spinal cord again. And again, I'm going to cut the spinal cord at C3. Okay? And I want you to tell me what the proprioception defect is. So if I have a hemisection of the cord, I lose proprioception where? On the same side. Okay? But now look, this is getting kind of fun here now. Okay, you already know that pain and temperature crosses on here. Okay? So now I want you to describe the combined sensory defect. I have the same cut, hemisection to cord at C3. Describe for me what that patient feels or doesn't feel. Okay, I lose pain and temperature from C3 down, so I can't feel anything in my arm and leg. I'm having pain sense in my arm and leg on the opposite side of my body, and I've lost proprioception on the same side. And that's called sensory dissociation. Sensory dissociation. And that's actually one of the ways that diagnostically we use to be able to tell what kind of a lesion, what kind of a pathology is occurring in the spinal cord.
Is it, you lose proprioception below C3?
Yeah, below C3. So at C3, I've already lost probably my hand, because the hand is like C7, 7, 8. And so I've lost the proprioception from that point down. So I've lost proprioception in my arm and leg on the same side, with pain and temperature on the opposite. Okay. Any questions? Okay. Well, this is a convenient place to stop. Y'all have a great weekend.